Professor Andrew Tolley from Case Western Reserve University. The title of his talk is Introduction to Infrared Modifications of Gravity. Galileons plus massive gravity. Let's welcome Professor Tolley.
Okay, thank you, and thanks for the invitation to come. And as Professor Rosen said earlier, there'll be a lot of overlap between what I'm going to talk about and her lectures as well, although we'll focus on slightly different topics. Today I'm going to be very basic and just give you some brief background on various different ideas that people have discussed for infrared modified theories of gravity. And then I'll get towards, I'll probably maybe not even get to today, towards Galileons and massive gravity, which will be my main focus. But I want to build up to why these things were even considered in the first place. And I'm going to start very basic. So let's even be even simpler and not even think about relativistic theories, but let's just work in the non-relativistic limit to start with. In other words, I'm going to consider situations where time derivatives are negligible, and I could basically approximate this stress energy just by its energy density. In other words, I'm looking inside the Newtonian limit for gravity. And so, as everybody knows, Newtonian gravity is described by Newtonian potential, like that. Or in field theory language, we can describe it by the following field theory. Here I'm writing down the energy in the field. So phi is going to be the Newtonian potential, and the energy in terms for the Newtonian gravitational field, that's the energy in the field, rad phi squared, just a simple field theory, and that will couple to rho, where rho is the mass density. So that's how you write down the field theory if you want, because I'm looking at a static system, I can look at the energy, but if you want to write down the action, of course, it's just the energy integrated over time, but because this is static, we might as well look at the energy. So that's a simple field theory, and varying that action gives the equation of motion, which is precisely the thing that if I'm looking at a point source will reproduce Newton's equation. So that's the Poisson equation, which gives you rise to Newtonian gravity. Now, I can formally solve this using Green's function methods, as everybody is familiar with. And I just need to know that the Green's function, the solution we get when we put a delta function in there, is a 1 over r form for the answer. So I can solve for the field using the Green's function method. Is just going to be 1 over mod r minus r prime, rho r prime, and there's a g in there. And that's the general solution for the Newtonian potential due to an arbitrary mass density source, as everybody knows. And so if I compute the actual energy in the gravitational field, which is this interaction energy plus the energy in the field itself, so I just plug this answer into that expression, then what I get is, the minus sign there, what I get is minus a half g, g is Newton's gravitational constant, integral to 3r, integral to 3r prime, rho r, 1 over r minus r prime, rho r prime. So that describes the interaction energy from an arbitrary distribution of matter. And this is effectively another way to encode the force law instead of this local field. Basically what I'm writing down is the analog of what in field theory would be called the generating function. Wj, which is given by the path integral, in which I add an external source. And here the external source you can think of as rho. Here is the mass density, and I'm looking at the analog of the generating functional evaluated at tree level. Okay, so that's just Newtonian gravity, nothing particularly strange there. Now, how might you modify that? Well, let's just think about modifying Newtonian gravity. Well, if we want to keep translation invariance and rotational invariance in the system, then the most general interaction you could write down in this generating functional form would look something like R prime, somewhat in a general weak field interaction between two sources, and then you would have an arbitrary function of the modulus of the distance between R and R prime. And so translation invariance guarantees that whatever this function is, it's a function of just the difference, and rotational invariance guarantees that it's just a function of the modulus. So that's the most general thing you could possibly do. And in this representation looks non-local. Of course, it already looked non-local here in the sense that I'm doing two integrals, but that's a red herring because I know I could have written it in terms of a local field theory. However, if I write down an arbitrary function here, I don't know that any local field theory would give rise to that. And we like to make sure that our field theories are local. And so really we're only interested in those special cases for which this thing would emerge from a local field theory. So what form does that have? Well, to give you that general form, let me first consider a special case of a local field theory which modifies the previous theory. And I guess I can use the blackboards. So let me simply do, let's make Newtonian gravity massive. I'm going to add a mass term to Newtonian gravity. And this is done very simply by taking this theory and adding an m squared, phi squared there. So that now describes the energy formula in a theory of massive gravity in the Newtonian limit. And that modifies the Poisson equation, gets a mass term. And let me get the sign right. Mass term comes in that way. And the effect of that is then now we have to solve this Green's function equation with a Laplacian here, minus m squared. And the answer to this is well known, and it was given earlier. We simply replace the 1 over r potential by a Yukawa potential. So if we add a mass to a graviton in this Newtonian theory, then we simply replace the Newtonian potential with Yukawa potential. Again, as everybody should be familiar with. So this prompts, in fact, a nice representation which I'm going to use, and which you can prove from field theory that the most general thing you can write down, the most general form of this energy between two sources in the weak field region that would come from a local and Lorentz invariant. Although here I'm in the static limit, so you don't see that it's Lorentz invariant theory, would take the following form. Instead of this expression, it would take the form of a superposition of Yukawa potentials, like this. this is the most general thing you can do. And what I'm doing is I'm borrowing something from field theory, which is called the Challen-Lehmann spectral representation. And from field theory, you can prove that if you start with a local Lorentz invariant theory, and then I'm just looking at the static potential, but there's a more general form of this that's usually used in the proof for the Challen-Lehmann spectral density. But from that, any form that comes from a local field theory of the interaction energy between two sources has to be written as a superposition of Yukawa potentials, in which that superposition is over positive masses for stability, and unitarity, which was also one of the assumptions. Unitarity requires that this quantity, which is called the spectral density, is positive. Now I'm slightly glossing over the story about spins, but I'll give you the more precise statement earlier. But in a non-relativistic theory, this is effectively what it is with God. So any modification of gravity, at least in this Newtonian limit, can be summarized by this statement for some spectral density d. Now, this is a statement not just at tree-level, classical level. This is a fully quantum field theory statement. So even if the fundamental particle propagating the force of gravity, whatever it is, even if it's massless or massive, so even if there's just a single particle, one graviton, even if it's massless or massive, when you include quantum corrections, so if it were just purely massless, you would expect that d would just be given by a delta function, or even if it were massive, it would just be some delta function at the value of the mass particle that propagates the force. But because of quantum corrections, this gets modified. There's a factor here in front, which is called the wave function renormalization. And this also then receives corrections from a continuous part, i.e. a part which isn't just a sum of delta functions from loop corrections and so on. So a generic theory typically takes that form. So the spectral density can have delta functions which correspond to poles in the propagator, but there can also be an extra continuous contribution. And I'll give you some examples of this. And this statement, what I've said so far, is true regardless of whether we're looking at UV modifications of gravity or infrared modifications of gravity. But this way of thinking about the force in terms of spectral densities is very useful. And I'll give you some examples of how this works out. Are there any questions on that so far? So hopefully that should be reasonably familiar. So let me start with the simplest example of a modified theory of gravity, and the original one in some sense, at least after Einstein, which is Kaluza-Klein theory, which you've heard about already today. And so Kaluza-Klein theory in its simplest form, I'm just going to keep things simple and think about one extra dimension, as was originally introduced. So Kaluza-Klein theory imagines that the universe is really 5-dimensional, and that 5-dimensional space splits up into 4-dimensional Minkowski space and a circle. So I'm going to parameterize my circle by a coordinate y, which will go from 0 to L, and then the L will be identified back with 0, so that describes the circle of circumference L. And I'm just going to look at this in the Newtonian limit. So this will be Kaluza-Klein theory for Newtonian gravity. So Newton could have done this, although he didn't. And so this is simply a field theory. Then instead of having 3 space dimensions, we're going to have 4 space dimensions. So the analog of that formula up there, we'll have now, we're going to separate out the ordinary 3 dimensions we think about, and then the extra dimension, y integrating from 0 to L. And just for normalization reasons, I'm going to put a 1 over L in there. That's just a normalization factor, so we cancel out the fact I'm integrating over length. And so my 5-dimensional Newtonian gravity theory would look like this. So essentially you replace effectively the Laplacian inside here, we replace phi squared with now plus a d phi dy squared because we have 1 extra space direction. And I'm going to couple that to the energy density. So this is a relatively straightforward modification of Newtonian gravity. And you all should be able to plug through it, but let me just go ahead. So now the Poisson equation is modified into this form. And as before, we can solve that with the Green's function method. So the analog of the Green's function, which determines the force between 2-point sources, like this. And now, as well as a delta 3r, we can have a delta in the y direction. And so, doing a standard Green's function solution, this is minus integral d3r prime, integral dy prime from 0 to L, Green's function ry, r prime y prime, rho r prime y prime. So that then the energy, once we plug that in, the energy, the interaction between 2 sources will have now 2 sets of 4-dimensional space integrals, 1 prime, and then we'll have rho ry, and then Green's function ry r prime y prime, rho r prime y prime. Okay, so it looks something like that. Now what does the Green's function look like? Well, it's pretty straightforward to do this because we've got 1 simple extra dimension. So to do that, do it over here. To do that, I just have to decompose the delta function.
One question.
Yes.
The integration is guaranteed to be convergent?
This integral? Well, yes, for any physical problem. So of course it depends on what the rows are, but the Green's function is perfectly well defined. So if you take any localized distribution of matter, the integral is always convergent. Yeah. Of course, as is well known, if you take this to be a sum of delta functions, then it's infinite because you have infinite self-energy and you have to perform renormalizations to subtract those out. But if you just take a smooth classical row, then it's finite. So it's finite modulo self-energy renormalization. Okay, so to solve this problem, what we can do is just use the expression for the delta function on a circle, which is just be given by a sum of Fourier modes. Because of the periodicity of a circle, we know that the Fourier modes are discrete, and because this must be periodic under L, then that determines the amount by which they're discrete, so it goes like 2 pi n over L, so when that shifts by L, this shifts by unity. So that's the expression from the delta function. And so by just writing G in terms of its Fourier modes, you can very quickly see that the formula for the Green's function has a 1 over L out there, 1 over mod r minus r prime, e to the minus mn mod r minus r prime e to the I 2 pi n over L y minus y prime, where mn are the famous Kaluza-Klein masses. These are the Kaluza-Klein modes. So what we're simply saying is that because we're in a circle, we have a Kaluza-Klein states which correspond to the various harmonic oscillations on the circle, and the full Green's function is given by a sum of Yukawa-type contributions from each of those states. You can think of each one as a separate particle. Each one gives rise to a Yukawa gravitational force, and so the total force from all those particles is given by a superposition of Yukawa potentials, precisely as promised, consistent with the Challen-Lehmann spectral representation that in general the force law will just be given by a superposition of Yukawa potentials. So this is a concrete realization of that fact. Now, as most of you know, if we look at this formula at large distances, so by that I mean if the separation between the 2 points is much greater than the size of the circle, then essentially this exponential from the Yukawa suppression is essentially 0, because these all go like 1 over L, and so if r minus r prime is much bigger than L, these are all exponentially suppressed, so we can essentially say these are 0, except for the one case, n equals 0, which is the Kaluza-Klein 0 mode. And so that's the usual statement that at large distances in this theory, or at low energies equivalently, then it'll just be the Kaluza-Klein 0 mode that will dominate the force. And that Kaluza-Klein 0 mode is the massless mode you would have just had in a 4-dimensional theory. So it's the statement that this theory at low energies will look 4-dimensional. And so then I could basically approximate this by just its 4-dimensional force law, 1 over mod r minus r prime. And when I plug that in to my formula for the energy, then at large distances, so that means when the two distributions of matter, looking at contributions from when these things are well separated, then essentially what you get is a force law that looks like 4-dimensional gravity, in which rho bar here is the average over the extra dimension. So it corresponds to the 0 mode of the matter source. This is the 0 mode of the matter source. So this is the Newtonian equivalent that at large distances will recover 4-dimensional gravity. But at small distances, i.e. in the ultraviolet, then what happens there at small distances is all the Kaluza-Klein modes are important, all potentially equally as important, because we're looking in the opposite region where the exponential is 1. And in that limit, it becomes a good approximation to do the standard trick of replacing the sum by an integral. And then in that limit, G is approximately, so it's helpful to do the integral separately from 0 to infinity and minus infinity to 0, just because of the modulus that would come inside the masses. So then we have e to the minus n 2 pi n over L, r minus r prime, r minus r prime, e to the I 2 pi n over L, y minus y prime, plus the sum from minus infinity to 0, which is actually equivalent to just replacing y minus y prime with minus y minus y. that integral is easy to do, the integral over n. Because it's just an exponential. And what you find is that g is approximately 1 over L. So we have an overall 1 over r minus r prime outside. And inside the integral, we can have a 1 over, let me take the number of 2 pi over L, so I'll bring out that in front. So that cancels that L. Put 2 pi there. And then I have mod r minus r prime minus I y minus y prime. And then from the second contribution, I have 1 plus 1 over mod r minus r prime plus I y minus y prime. And then that gives 1 over pi. And you complete the square, and the y's drop out, and you complete the square, and you simply get r minus r prime squared plus y minus y prime squared, which is just the standard Newtonian potential in 5 dimensions. So this confirms the fact that Fluxus-Klein theory is an ultraviolet modification of gravity, in which at low energies it looks 4-dimensional, and at high energies it looks 5-dimensional in this case. And that generalizes, of course, to these more complicated compactifications, where if you're in 11-dimensional supergravity, then at high energies you sum the Fluxus-Klein tau and you'll recover the 11-dimensional force law, and the lower energies you'll recover the 4-dimensional force law in which the massless modes dominate. So all of this is reproduced by the full standard Fluxus-Klein theory, and this was probably the most well-known way to modify gravity for a long period of time, until, let's say 15 years ago or something, till a different idea, a slightly different idea is what I'll call warped compactifications. And this was the idea made most famous by the so-called Randall-Sundrum model, which was around 1999. And so let me think about what the Newtonian limit of the Randall-Sundrum model is. So here the idea is we're also going to imagine that there's one extra dimension for simplicity. So we're in 5 dimensions. But in this case, instead of the 5th dimension being wrapped on a circle, the 5th dimension will be infinite. Now that's a slightly bizarre thing to do, because the fact that the 5th dimension was finite and small was crucial to have a region where we recovered 4-dimensional gravity. But here you can do the same thing by having warped geometry, where we're going to take the 5-dimensional space to be AES5, so anti-de Sitter space in 5 dimensions, use metric in appropriate form. It can be written as so. And this is warped in the sense from this warping factor here. So y is the extra dimension, and as we move across the extra dimension, the size of the 4-dimensional space gets smaller if we're increasing y. And then we're going to imagine that there's a brane localized at y equals 0. So the picture is something like this. We have a brane at y equals 0, and then the metric falls off exponentially away from that as y goes out to infinity. So this is an example of a brane world construction, which was motivated by the branes that arise in string theory, although in the particular case of the Randall-Sundrum model, it was being thought of out of the context of string theory, but you